event. Dr. L. Vidya Madam, who is the senior faculty member in our PG and Research Department of Mathematics. She has completed PhD in the year 2018. Also, she has passed set examination. She has more than 13 years of experience in teaching. Also, she has 5 years of experience in research. And I feel honored to welcome our beloved principal, Dr. M. Lakshmanaswamy sir, and our respected Chief Executive Officer, Dr. V. Sinnaswamy sir, and our Honorable Dean, R&D, Dr. S. Balaswamy sir, for this webinar. Once again, I welcome you all for this webinar series. Thank you.
Thank you, sir, for your nice words. Now I request Dr. L. Vidyarani Madam to present her findings. Thank you, Madam.
Very good afternoon to one and all. It's a great pleasure to be part of this webinar series. First, I thank President Archami sir, Secretary and Director CA Vasagi Madam, Principal Lakshmanaswamy sir, Dean Research and Development Balaswamy sir, convener of this webinar series Vijayalakshmi Madam, Coordinator Vigneshwaran sir, and the organizing secretaries Revati Bala ma'am and Senthil Kumar sir for giving me this wonderful opportunity to be part of this webinar series at this quarantine period. So the topic what I have chosen is topology, an approach using Intuitionistic set. So topology, it's real mathematics. It has developed so much. So many sets have been introduced in topology. The set what I'm going to introduce today is Intuitionistic set. So before going into that, first let me recall what topology is. What is the meaning of topology? What the word topology literally means? Why is the name topology? How it differs from the other names? We always speak that topology, it is always studying objects. So even in geometry, we study about objects. So what is the difference between geometry and topology? So topology, it is a branch of mathematics in which we study shapes. Even in geometry, we study shapes. For example, let me tell you, we have triangles, circles, and so on. Video. Okay, topology, it's study of shapes. So I'll tell you with an example. I have an object with me now. So everyone know, can everyone see this? So I have an object with me. So this is an object. I don't say that it is a rubber band. I say it's an object, a kind of circle. So I'm just expanding it. So if I expand, I have the same object with another shape. If we are learning this in geometry, we say that the first object what I shown was it is circle, and the second image after making the transformation I showed you, this was an ellipse or an oval. So in geometry, we say that to be the circle and this one to be an ellipse or oval, and we study their own properties. Circle has its own property, and oval, it has its own property. So here a circle, it has been deformed to oval. I'm stretching it and I'm deforming it to oval. So a shape has been deformed to another shape as an oval. So there is a change in the shape. If it is a geometry, we always say this shape, it is different from the shape what I have deformed, because in geometry always we consider the measurements, either the radius or area or surface or length or breadth, whatever it is, always we consider about measurements in geometry. But in topology, we never consider about measurements. So this shape, it has been deformed to another shape, even though I say that this is a topology. The reason is, when I am transforming, there may be some invariant properties, variant properties as well as invariant properties. That is, the properties of this object when it is a circle, when it is transformed to an oval, it will have some similar properties as well as some dissimilar properties, some invariant properties. So when it is transformed, we are going to study the properties which are invariant after this transformation, after this deformation. Studying those properties, you call it as topology. I'll show another example. See, I have a ball with me. So dimension of this ball, so it is a sphere actually. Sphere, even this, see, I have put some lines on the sphere. I am enlarging this on the lines of the sphere. See, if I enlarge it, see, I'm expanding it, I'm stretching it. Assume that, see, since this ball, I couldn't stretch it, assume that I'm stretching it on the lines of the sphere. So I'm stretching it. After stretching it, you will get a sphere with those edges. So after stretching it, this sphere, it is deformed to another shape. You call that a cube. So this is transformed to a cube. Even though this is transformed to a cube, I say those two shapes, they are topologically equal. I don't say that shapes are equal. We say that they are topologically equal. So this is transformed to a cube. It is topologically the same, because topology, we are studying the shapes of the objects which is invariant. That is the properties which are invariant. Studying those properties, you call it as topology. So one is transformed to another. See, so in topology, I'll go in depth into it. So in topology, the most important property, it is homeomorphism. So to have homeomorphism, always you need a mapping. So whenever you there is a transformation between an object to another object, there is mapping. So this point, it is transformed to another point which is on that particular object. So it will have its pre-image. So you will have the corresponding points between those two objects. So surely there will be mappings between those two objects. So if there is mapping, I can find whether it is homeomorphic. If it is homeomorphic, then the properties, topological properties that are satisfied by this object, it will also be satisfied by the object which has been deformed from this object. So one important thing, I told you this is deformed. So I told you can stretch it or you can crumble it. The two things that should not be done is you should not tear it. See, I have a circle. See, circle here. I cannot cut this, and if I cut this, it will be a line. So this circle and a line, they are not topologically equal, since I'm cutting it, I'm tearing it, right? So to study topological properties, a shape that is deformed. So while deforming those shapes, you should not either cut it or never you should glue it. Say you have a line, you cannot glue that line and you cannot make a circle. So you should not glue it or tear it. So that deformation should not be in that way. So now let me go into the slides. Okay, now I have gone into my presentation. So what I'm going to present today, I have given an overview. So when when was the topology got its origin? What are the branches? What is the little definition of topology? What are the various fields in topology? How you can take your researches in those fields? What intuitionistic set is? So always initially topology, it was defined using the crisp set, the well-defined set what we are using. But I am going to say how an intuitionistic set can be used in topology, what are the properties of intuitionistic set, and how to define an intuitionistic topology. So the origin, Johann Benedict Listing, he was the one who introduced the term topology in the 19th century, and actually it later came into existence only in 20th century. So as I told you, topology, it is began with the study of curves, surfaces, and other objects in the plane, and three spaces in the beginning. Topology studies properties of spaces that are invariant under any continuous deformation. So you're deforming it, invariant properties you're studying those properties, you call it as topology. So that's the reason you call it as even rubber sheet geometry. So the objects of topology are often formally defined as topological spaces. I told you homeomorphism, it is the most important property of topology. If two spaces or two objects, if they are homeomorphic, then it is said to be topological. There exists homeomorphism between the two objects or these spaces. So branches of topology, there are various branches of topology. General topology, that's the thing what we are going to see, where it deals with points and set and the set theoretic definitions. So there is algebraic topology. It is a branch which uses tools from abstract algebra. So differential topology, it is used in the field of differential equations, where you have differential functions. Then the geometric topology, it's used to study the manifolds and the functions between those manifolds. So metric topology, as the name indicates, metric distance or you have some quantity. So metric topology, it is induced in the metric. Using those metric that is defined in the topology. So that's the metric topology. So the topology, what we are going to discuss now is point set topology, where we are dealing with point sets, the functions between them, the various connectedness, compact properties of the topologies. So in that, I'm going to introduce intuitionistic set. Instead of crisp set, how an intuitionistic set can be used. So a definition of the topology. So always we see the definition of topology. It has been said that a collection, first you need a set. So and that set, it should be non-empty. I am considering a subcollection of that set. Subcollection of that set should satisfy three conditions. First condition is whole set and null set should be within that set, and arbitrary union of that set should also belong to that set. Finite intersection of sets should also belong to that set. See, you have two things. One, union we consider arbitrary, which means either you may have a finite or infinite. But while considering intersection, we don't take arbitrary intersection. Even that has a reason. We should consider only the finite intersection. So if you consider arbitrary, wherein you will have infinite points, so there it may not belong to the the subset tau. So let me say that even with an example. So consider an open set. Always we know that we study real analysis, or an open interval, it is an open set. So if you consider an open set 1 and 1, 2, 2, it doesn't belong to it. So its neighbor 2, it is always not included with the set. So its neighbor 2 minus epsilon alone, it belongs to. So let me consider its neighborhood is some 2 minus some minus 1 by n. If n tends to infinity, so suppose if put arbitrary intersection, and if n tends to infinity, then it becomes 0 and 2 will be included, and it becomes that part alone, it becomes closed, and that will be included in the set. So which should not be there. And always topology we consider open sets. So first thing, there should be a set which should not be empty. We should consider a non-empty set. I am considering a subcollection of that set, and that subcollection should satisfy these three conditions. Non-empty set in X should be there. Arbitrary union of sets should be in that set. Finite intersection of collection of that set should also be within the set. That collection with the set what you are considering. So X comma tau, you call it as topological space. So now I have found out a collection which satisfies all these three properties. So that collection of sets, you call it as open sets. And if you take complement for that set, it is closed set. Okay, the next one is types of topology. Since I'm going to consider the points and sets, I have taken discrete and indiscrete. You have still more topologies, cofinite topology. You have still more which have been defined in the real line. So here I am considering, I have given two types. One is discrete topology and the another one is indiscrete topology. So what does that mean? So I told topology, to find that topology, you need a non-empty set. I am considering a subcollection. So and that subcollection should satisfy three conditions. And that if it satisfies those three conditions, you call that collection to be the open set. And that is the topology with combined with X. So X comma tau, you call it as a topological space. So that subcollection, if it consists of all the subsets of X, that is the power set of X, you call it as discrete topology. Indiscrete or trivial topology, obviously if X and phi alone is there, that alone will satisfy all the three conditions. So if you have X and phi, then that is indiscrete topology or the trivial topology. So the most important property in topology is homeomorphism. So to find out whether two objects, two surfaces are homeomorphic, you need a function between those two. So to find whether those two surfaces are homeomorphic, first we need a function. So I'm defining a function f from x to y, where x and y both should be the topological spaces. So x and y, they are topological spaces. F is a mapping between x and y. So to check whether they are homeomorphic, this function should satisfy those two conditions. It should be a bijective map. You know that bijective map, it is one-to-one and onto. Then f and f inverse should also be continuous. That is, f should also be continuous. F inverse should also be continuous. If these three conditions exist, then there is an homeomorphism between two surfaces. So one surface, it is homeomorphic to the another surface. One topological space, it is homeomorphic to the another surface. If it is so, if they are homeomorphic, they are topologically equivalent. I told you, when circle it is transformed, we say they are topologically equal. So in that way, if there exists an homeomorphism between two surfaces, so that's the reason topology came into existence. Suppose we couldn't find the properties of an object, to find out the properties of that object that has been projected to someone, which could be in which properties can be found out. If those two are homeomorphic, then the properties of that object can be found out with the objects what the people have. So various fields in topology. So general topology, that was the topology, what I said, which should satisfy three conditions. So this was introduced initially. That is, relaxation of the conditions with those topologies arise to the following ones. So the supra topology, in the Mashover introduced it. In that, the union condition alone is considered, intersection is not considered. So relaxation of the properties. You have three properties there to be, that is in topology, you have three things, X and phi should be there, union, arbitrary union should be there, and finite intersection should be there. So in that, finite intersection alone is removed. So that came arise to supratopology. Generalized topology, similar to supratopology. In supratopology, we consider the whole set. Even in generalized topology, intersection part is removed. So X and phi and union part alone we will have it in supratopology. In generalized topology, X has been removed. By topology, we consider two topological spaces. So these are the various fields remaining fuzzy, those fuzzy sets introduced with these topologies. So I'll show that in the next slide. So next, the remaining parts, fuzzy topology, which means fuzzy set that has been introduced, put up in the topological spaces. The set we are considering is different. So in the topologies, general topology, supratopology, generalized topology, bitopology, in all these things we will consider the well-defined crisp sets, whereas different types of sets put upon on those topologies came arise to various topological spaces. So fuzzy set, it was introduced by Zade in 1965, and Chang introduced the fuzzy set what Zade introduced in the topological spaces, and fuzzy topological space, it was introduced by Chang in 1968. So digital topology, so it's in the field of pictures, that is digital images, 2D and 3D images, studying about the connectedness. So in digital topology, same thing, the union condition, intersection conditions are satisfied or not, that has been put up, and it is studied in the images. It was introduced by Rosenfield in 1975. Rough set, it was introduced by Palek in 1982, and it was put up on the topological spaces by Lily Zivagar, I think. And soft topology, it was introduced by Malsov in 1999, and Shabir and Nas introduced soft sets in the topological spaces in the year 2011. Ideal topology, Jankovic and Hamlet introduced in the year 1990. So the topology, what I'm going to deal with is Intuitionistic topology. It was introduced by Dogen Coker. Actually, he introduced Intuitionistic set in the year 1996, and that set has been put up in topology in the year 2000. And Lily Zivagar, he introduced nano topology in the year 2013. Nutrosophic set, it was introduced by Smarendaki in 1995, and Nutrosophic topological spaces was introduced by A. Salma and Alblovi in the year 2012. So Intuitionistic set. So it was introduced by, as I told before, it was introduced by Dogen Coker in the year 1996. And he himself introduced this set in topological spaces in the year 2000. So next comes what Intuitionistic set is. Intuitionistic set, see how there should be some difference between the set what newly comes and the existing crisp set. So Intuitionistic set, it is different from the existing classical or the crisp set, but it has been derived from the crisp set, existing crisp sets only. So first, let me tell you an example, and let's go for the definition. Let me consider a class. So in a class, there are some 50 students, and they go for an exam. In that, some 45 students get through. So 45 students get through, and 4 they fail. One, he or she is not attending the exam. So suppose if I want the number of students who get through in the examination. So my set is a class, suppose some mathematics class or physics class or whatever it is. In a class, so that is my set. Always it is well defined. You have students, you have male, female students, it is well defined. So in that set, I am considering the number of students passed. That what I want is number of students passed. So that will be the member what I'm going to consider. So always I'm considering the number of students passed. Automatically, its complement would be the number of students those who fail. So that will be the non-member. So let's come to the definition of Intuitionistic set now. So X, it is a non-empty set. So I told you in a class. So a class you will have some students. So X is a non-empty set. So Intuitionistic set A, it is an object having the form A. So that's the notation of the Intuitionistic set. You're denoting it with the angle bracket. X denotes the set what you're considering, the well-defined set what you're considering. Suppose, for example, it is a class. So X, the whole set, in that always the first one will be the member. So suppose if the number of students get through is the thing what I want is, so that will be the member. And A2, it will be the non-member. So non-member, so for example, suppose if it is failed. And one thing, A1 and A2, if you take intersection, it should be empty. So if suppose students are going for an examination, if he passes, if he get through, he will never fail. If he fails, he will not get through. So always the intersection of those two, it should be empty. So A1 you call as member of A and A2 the non-member of A. So I'm showing an example. Let X is equal to A comma B. You have two elements here. An Intuitionistic say is X single element A and B. So A is the singleton A is a member of A and singleton B is non-member of A. So its intersection, it is empty. So it should always be empty. So always in the whole set, in crisp sets or the classical sets, you will always consider the whole set what you're considering. So if X is equal to AB, that is the whole set. But in the Intuitionistic notation, that is not the whole set. You're denoting it by a symbol X tilde. X, that is the set what you're considering. So always first thing should be the member and the second one should be the non-member. So X, it is a member. Since it is a whole set, I'm considering the whole X. And the empty, its complement. Similarly, null set X, phi and X. Always, so in while considering the normal sets, so power set, it will consider 2 power n elements, right? But in the Intuitionistic set, it is not so. You will have 3 power n elements in the power set. So I'm showing that by an example. X is equal to A comma B. Here you have 2 elements. So 3 square, you have 9 elements. So possible subsets, the condition is first one is always the member. Second one is the non-member. If you take intersection of those two, it should be empty. You have 2, so A and B. For example, consider there are 2 persons. So A is 1 person and B is 1 person. They are going for an examination. So I am considering the pass. So if A gets pass and B gets failed. So that set is A and B. There are 9 possibilities. So A is getting pass, B is getting fail. The another one is B is getting pass and A is getting fail. The another one is A is not at all attending the exam and B is getting fail. So that is X, phi and B. And the another one, the fourth one, X, A, B, which means A is passing and the B, he is not at all attending the exam. B is passing, A is not at all attending the exam. So in such way, so you can calculate it or you can think over it. So you will have 9 such Intuitionistic elements. So I have given an example if you have 3 elements also. Suppose if you have 3 elements, if it is a classical set, crisp set, you will have 2 cube, then it is 8 elements. But here you have 27 subsets in an Intuitionistic set. So that's the thing I have given it in the example. So next, let's come to the properties of Intuitionistic set. So the set theoretic properties, what all the set crisp set or the classical set satisfies, even intuitionistic set satisfies. But here some properties it is not getting satisfied. Let's see that one by one. So X is a non-empty set. Here we are considering two sets, two intuitionistic sets, X, A1, A2, where A1 is a member and A2 is non-member. B is another set where B1 is member and B2 it is non-member. Generally, if we consider AI, where from the set X, AI to the power 1, that is the member, and the other one it is non-member. So let's check out the properties with the example. So if A is subset of B, if A1 is subset of B1 and A2 contains B2. So always in the classical set we say that if A is subset of B, the elements in A should be within B. So here, since we have member and non-member, we have to consider the members of both the sets and the non-members of both the sets. So to find out the relation A subset of B, we are considering member as well as non-member. I'm showing that by an example. So X is A, B, C. It has 3 elements. I'm considering 2 intuitionistic subsets. So X, phi, AB, it is an intuitionistic subset. B, X, B, C, A, it is also an intuitionistic set. Since the intersection of member and non-member, it is empty. So you have to check whether it is subset. So to check A is subset of B, you have to consider the members first. Member of A should be the subset of member of B. So here phi is subset of B comma C. So it is subset. Non-member of A should contain the non-member of B. Here non-member of A is A comma B and non-member of B is A. So it contains A comma B. Dear participants, suppose if you have papers with you, you can note it down. Only if you note it or you can write it simultaneously, you will know how the operations are being done. So phi is subset of BC and A comma B contains A. So member of A should be contained in member of B. Non-member of A should contain the non-member of A. If those 2 conditions are satisfied, you say that A is subset of B. So the next property, if A is equal to B, then A should be subset of B and B should be subset of A as usual, but the checking property alone varies. A subset of B, here if A should be subset of B, member of A should be the subset of member of B and non-member of A should contain non-member of B. Similarly, for a subset B to be the subset of A, member of B should be the subset of member of A and non-member of B should contain the non-member of A. So both the conditions, those are satisfied. So here A is equal to B. So complement of an intuitionistic set, you will interchange the member and the non-member. When the member and the non-member gets interchanged, that becomes complement of that intuitionistic set. So X is A comma B comma C. X, intuitionistic set A is X, phi and AB. You are interchanging the member and non-member. That becomes its complement. Union and intersection of intuitionistic set. So same thing, whenever we operate some operations on intuitionistic set, always we will consider the member sets as well as the non-member sets. So A union B, the set we will concentrate on the member of that set. So A union B, so union should be taken for the members. So if you have 2 sets A and B, you need to find the union of A and B. You're taking union of the members and the intersection of non-members. See, A is X, B singleton A, and B is X singleton C, A comma B. Members of both the sets, you're taking union, and non-members, you're taking intersection. Similarly, for intersection, members you should take intersection and non-members you should take union. So I have given in general union. If you consider more sets, members you should take union and intersection should be taken for the non-members. So A difference B, that is A intersection B complement. So I'm showing that with an example. So A, B, and C. Even this property, it has been satisfied by the classical set. So we are checking out whether even intuitionistic set satisfies those properties. So A difference B, it is A intersection B complement. B complement, as we know it, interchanging the member and non-member. So A difference B, it is X singleton B and phi. So these are the operators. Necessity operator, you call that square bracket A, it is, suppose always I told you we will consider the member functions. So A1 is a member, and non-member if it is A complement. See, we have seen examples before. Member, we are considering a member. Non-member need not be always its complement. So A, comma B and C. So there we have complements. Always it need not be its complement, complement of the member. Non-member need not be the complement of the member. So necessity operator, member, if non-member is its complement, you denote it with the necessity operator. And the facilitating operator, that angle bracket, suppose if the member is the complement of the non-member, you're denoting, even you have the operations, you can take facilitating operator with the necessity operator with the facilitating operator. See, union of, intersection, union of. Similarly, you can apply even those operators. Intuitionistic whole set, I told you before, it is not as usual. X phi, it is the whole set, and X phi X is the intuitionistic null set. Still, you have the basic properties of inclusion and complementation. A subset of B and B subset of B, obviously, it implies A is subset of C. Let's see that X is A, B, and C. I'm considering a set X, singleton B and AC. B is X, singleton B, singleton A. C is X, B, comma C, and singleton A. So A subset of B. So to check whether A is subset of B, you will consider the members. Member of A should be the subset of member of B, and member of A should contain, non-member of A should contain the non-member of B. So you're checking, putting up the conditions, checked, it is subset. So similarly, it doesn't mean that only one set should be subset of B if there are more than one set. So AI sets or the subsets of B, then the whole collection, whole union of those sets also will be the subset of B. Similarly, if B is subset of some collections, A1, B subset of A1, B subset of A2, B subset of A3, B subset of A4, and so on, then B will also be the subset of intersection of AI. So complement, union of AI, the whole complement, it is intersection of AI complement. So you should know how union has to be taken and how intersection has to be taken. If you are well versed in these operations, you can operate it. So intersection of AI whole bar, it is union of AI bar. So that it's complement. So A is subset of B if and only if B bar is subset of A bar. So I have shown that with the example. A complement, its whole complement, that is equal to A. So that is also, it's true. If you take complement for the null set and the whole set, that is also true. So I told you some properties which are satisfied by the classical set are not satisfied. So this is the one property which is not satisfied. So always we knew it. If there is a set A and complement of a set A, it's, if you take intersection, always it will be equal to null set. But it is not true here. A intersection A complement need not be equal to the intuitionistic null set. See, let's see that with the example. So X is A, B, C. You have a set A, X is B and singleton B and singleton A. Intersection of member and non-member, it is empty. It's complement. So I have made a mistake here. Actually, it should be A and B. Then A and B, if you take intersection, you will get null set. you will not get AC. Actually, there should be A comma B. I have made a mistake here. A complement is A comma singleton A comma singleton B. You're just interchanging the member and non-member. So X phi, it should be A comma B. So even though whatever it is not equal to null set, because intuitionistic null set, it is denoted by X phi X. So phi should be the member and X should be the non-member, but it is not so here. So it is not true. So A intersection A complement is not equal to null set in intuitionistic set. So this is, I have given some properties. Still you have so many properties. You can define functions, mappings. You can check whether it is continuous. There are so many, one operator can be applied on the other. For that, you can refer the paper published Intuitionistic Set, titled Intuitionistic Set by Dohan Coker, to check the remaining properties, and you can work on that too. So intuitionistic topology, which means already I told you there are different topologies: topology, supratopology, generalized topology. Therein we are applying different types of sets. So here in topological spaces, we are going to apply intuitionistic set to bring out the intuitionistic topology. So same thing, you're having a collection X, and you're finding out the intuitionistic subsets of X. And if the whole set X and the null set phi in the intuitionistic set, if it belongs to that subcollection, union of collection also belongs to that collection, infinite intersection also belongs to that collection, then X comma tau, you call it as intuitionistic topological space, denoting it by ITS. You're putting intuitionistic set on that topological space. So you call that space to be intuitionistic topological space. So elements of tau, you call it as intuitionistic open sets, and its complement intuitionistic closed set. So I have given an example how to define an intuitionistic topological space. So X is ABC. You have a collection, subcollection tau, the whole set, intuitionistic whole set, intuitionistic null set, A1 and A2. In two ways you can define. So A1 and A2, where A1 is an intuitionistic set, X, AC, and A2 is X, AB, comma, phi. So union, if you take union, it should be within the set. If you take intersection, even that should be within the set. So union, so while considering union, you should do it carefully. You will consider it for members, and for intersection, you will consider it for non-members. So union should be within the set. Intersection also should be within the set. That subcollection, you call it as the open set. Together with X, you call it as intuitionistic topological space. So similar way, we can find out the closed set. It's taking its complement. Taking for an intuitionistic set, taking its complement is interchanging member and the non-member. So intuitionistic interior and closure, as usual, we are considering the open set to find the interior, and closed set for finding out the closure. The only difference is we are considering the intuitionistic sets. So to find the closure, X is ABC, you have a collection tau closed, that is the closed set. A is X, A, and C, intuitionistic set, finding out the closure. So closure, intuitionistic closure is intersection of collection of sets that contains the set A. So that is the closure. So let's check it out. A, X, A, and C. So to find out closure, always you will consider the intuitionistic closed set. So you have to check which are all the sets which contains A. So the set which contains A is only X. So obviously taking intersection, you will get X, the intuitionistic whole set X. And in the topology, always you know that if a set is closed, then closure of A will be equal to A. Even that property, it is satisfied by intuitionistic set. So that I have given it in the example. So considering C is X, C, and A, it is closed. it is in the closed set. So while taking closure, you're getting the same thing. So that property which is satisfied by, which is true in the topological spaces using the crisp set is also true using the intuitionistic set. So similarly, finding out the interior. So to find interior, you will consider the open set. So X is, you have three elements A, B, C. We have constructed a topology X null set, X singleton A, singleton C, X, A, B, and null set, and its complement intuitionistic closed set. So A is X singleton A, singleton C. So here also, to show that if it is an open set, then interior of A will also be equal to A. So to show that, I have put an example. So X singleton A, singleton C, it is open. So it is an element of tau. So while taking interior, it is equal. So X singleton A and singleton C you're getting while taking interior, it is also equal. So X null set and A taking interior, that is, to find out the interior, you have to find out the sets which is contained in B, and you have to take union. So no other sets other than null set is contained in B. So that is the interior of B. Thank you. Actually, this is not the end of this. These sets you can use to find various properties, compactness, connectedness, all the properties of the topological spaces. Not only in topology, even you can apply this in various other topologies. I told you have by relaxing the conditions, you have supra topology. In that relaxing X, you have generalized topology. Not only in that, you can apply in ideal topology. You're applying these sets to find out various topologies. So these sets, it can be used for further research. Thank you.
Thank you very much, madam, for your fantastic presentation. As a topologist, I convey my regards to you. The participants can post their queries or clarifications in the chat box. The first question, madam, posted by Dr. Vijay Lakshmi. Any applications regarding your set?
Okay. Actually, I told you, intuitionistic set, in all the applications, in all the spaces, we need not always consider all the points. Sometimes we may reject some points, and we need to consider only some points to find out its properties. In such cases, you can use this type of set, intuitionistic set.
I think the same answer will be applicable to the queries raised by Sivakumar Karupanan and Nitya Kalyani Sridharan. Okay, no questions in the chat box. I request Dr. C. Ravichandran, Assistant Professor of Mathematics, to propose the vote of thanks. Sir, please.
A very good afternoon to everyone present here. On behalf of all, we deem it a great honor and privilege to propose the words of gratitude for being with us this afternoon and making us feel proud and more than above your love for us. On the recollection of so many great favor and blessings, we now with a high sense of gratitude offer up our sincere thanks to the Almighty, the Creator and the Preserver. My hearty thanks to our chief guest, Dr. L. Vidyarani Madam, for gracing today's session and delivering a wonderful lecture. Thank you for your very interesting lecture, Madam. I am sure that all the participants have taken note of your suggestions and will be discussing within their organizations the action to be initiated at their level. We extend our sincere thanks to our respected President Dr. M. Archami sir and our Honorable Secretary and Director Dr. C. A. Vasugi Madam for the desires and wonders of young generations and sharpening the educational agenda. Dear Madam, your actions inspire others and you explore the possibilities and help us to reach the new horizon. We take immense pleasure in thanking our beloved Principal Dr. M. Lachimnasamy sir and CEO Dr. B. Chinnasamy sir for their great support and guidance. Thank you, sir. With deep gratitude, we would like to thank our Dean R&D Dr. S. Baluswamy sir for providing us with all the possible support towards this faculty development program. I also extend thanks to convener Dr. D. Vijayalakshmi Madam, coordinator Dr. M. Vigneswaran Sir, and organizing secretaries Dr. M. Revati Bala Madam and Mr. N. Sendil Kumar Sir, and our all the staff members and research scholars for their support and cooperation to make this faculty development program a grand success. Last but not the least, I thank all the participants for showing their interest in this program. Once again, thank you very much all.
Thank you, sir, for your nice words. The participants are requested to join on tomorrow by 9:45 a.m. Tomorrow we will have two technical sessions. The first session will be handled by Dr. R. Manimegalai, Assistant Professor of Chemistry. The topic is Futuristic Trends in Nanoscience and Technology. And the second session will be handled by Dr. K. Soundararajan, Assistant Professor of Botany, on influence of fragrance on human electropine activity. Thank you for the patient listening. Have a nice day.